my website at that address, so they're existing now. Those are our email addresses, and this is a talk to ANPA by Zoom. Right, outline of talk. Yes, so, well, the natural numbers, I think we would say they're not really natural in a category theory sense, where natural would really have 3 levels of definition to define anything. So we think they're a bit of a misnomer. And we come up with this idea of ordinary numbers, which are on the lowest rung of our 3 realities. And ordinary numbers, in fact, are all numbers bar 3 when we do our analysis. And so ordinary numbers would be what are normally called the natural numbers, integers, reals. Ordinary number 0, that doesn't count as a fully fledged number. Neither do -1 and infinity. And the top rung, really real numbers we come out with are 1, representing the universe, E, representing Euler's number exponentiation, and pi. We can come up with some pretty good category theory reasons for 1 and E. Pi is more because it appears to pervade everything. And so those are our top rung numbers. And we're going to give some examples of first order methods relying on number, which we think are flawed to some extent. We're very ingenious scientists. We can do an awful lot with first order methods, but we think that for future things, burning issues like this virus pandemic control and climate change, for instance, we really ought to be getting on to higher order methods for doing things. Well, I did actually, as I added this bit to the talk that Mike sent around. So I looked up natural on the web, and most of the examples seem to deal with counts of sheep in fields, which is quite interesting. I'm really qualified as a Northumberland person on this, because there are more sheep in Northumberland than people. So it does have some local relevance. There are lots of arguments about natural numbers. Mathematicians used to start them as 1. And when computing science came along, we said, no, you've got to start at 0, because we want to count from, it's basically counting this. And mathematicians counted from 1 upwards in the integers. In computing science, we want to count upwards from 0. And Peano's axioms for generating infinite sets, they're well known. That's controversial in some circles, perhaps, although everyone who accepts infinity would agree with Peano's axioms. But if you go in for finite sets, then you have a few more worries. So what about defining natural numbers by arrows? Well, of course, there is a way of doing that, and that's with the successor function, where we have f0 equals a, and then you apply f1 SA and f2 SSA, and so on. So you can do a successor function through the natural numbers. And another thing I looked at was the natural numbers object, which comes from category theory and after Lovia. And this is a very well-known construction in category theory. You've got n there. Sorry, I'll move the. There we are. You've got n there going for a successor function to the next value of n. In category theory, it's got to be in the context of another object. So the object, other object we're choosing is A, and then you have these. One is the terminal object. Then you have these equations. The diagram. You have these equations that have to be satisfied. U times Z equals Q, and FU times U times equals U times S. You could argue what the equals means there. I think Michael will probably be, might be a bit critical of the equal sign appearing so early on. But so that's a very popular construction for giving natural numbers. It rather conflicts with our talk today, though, in that this is really categorification of what happens in sets. And categorification is something that we don't really like. We prefer category theories that come from a basic theory of arrows and categories, rather than something that's a straight translation from set theory into category theory. So we're not really recommending that, but obviously category theory does have quite a lot of, right. So is Wigner's enormous usefulness of mathematics really something bordering on the mysterious with no rational explanation? The idea there is Wigner, mathematics seems to be more successful than it really deserves to be in some cases. That's something in the background. Kronecker is of interest. He, of course, was interested in finitistic mathematics, finite mathematics, and he actually is an early lead-in to intuitionistic approaches, which we're going to deal with today. So the basic logic that we're dealing with is not Boolean, it is intuitionistic. ANPA from its beginning has been fascinated by the integers, of which a combinatorial hierarchy may be able to provide values for both the fine structure constant and that of Newton's universal gravitational with the Parker-Rhodes conjunction within 0.03% of the known experimental value. But the reason for any Wigner coincidence awaits explanation, but so does that for most significant number theory. So these are sort of problems with numbers we've got. Numbers known as the reals are hardly real except in the mind, but rather first order models. We're not denying the existence of these numbers, we're just saying they're first order models relying on reductionist assumptions, and will, for convenience here, will be referred to as ordinary numbers. These cannot be reliably applied to higher order phenomena where most of today's problems lie. So arithmetic is always first order, algebra is only generalized arithmetic, and things like topology, which claim to be higher order, are really just dressing up set theory with things like open subsets, rather than being inherently above first order. And the same characterizes more sophisticated numbers like tensors, surreals, Hilbert spaces, or Einstein's field equations. They're all only valid.
Excuse me, could I ask a question? Of
course you can.
What do you mean by higher order phenomena?
Well, higher order is basically mapping from one function to another. So if you have first order, you have a function, a higher order would be mapping that function to another function, as in a functor. And if you map that functor to another functor, you have a natural transformation, which is the top level of mapping.
Thank you.
Yeah, so that's basically what we mean. It's mapping from function to function. Okay? Problems with numbers 3. So obviously our philosophy is based quite a lot on that of Whitehead, Alfred North Whitehead, who of course, in a sense, started off with numbers in the Principia Mathematica, and then in the end decided it couldn't be done, that the Principia Mathematica was not the way forward for maths, and so he went to metaphysics. The trouble is he went to metaphysics without having a new mathematics to go with it. Category theory wasn't invented then, or hadn't been developed then. And so we think that a lot of people are still stuck in set theory when maybe other branches of mathematics should be looked at more seriously. So Whitehead's process, yes, early ANPA followed the 20th century science in treating the reals as isomorphic to sets, from which it follows that the number 2 exists as an exact integer in nature, as evidenced by Newton's inverse square law. But Whitehead had by the 1920s moved to process as the controlling force of the universe. And in fact, you'll note that our website is actually, the top directory is called process. So we are actually, I wouldn't say disciples of Whitehead, but we certainly are guided a lot by Whitehead as to how we think science should develop. And Ted Bastin, one of the founders of ANPA, advocated process at the time, but while still adhering to Newton. So Whitehead didn't actually believe in Newton's three laws of motions. He didn't like the Euclidean assumptions in the first law, and he thought the second law was circular in that it assumed the answer at the start. Even current mainstream cosmologists take the view that the universe departs from the Euclidean by about 2%, they estimate. However, this figure may be too low. That is more likely to be related to the value of the Euler number, E. E is an important number. So assumptions are one of the great problems in science everywhere, really. And one of the important principles of ANPA was to consider coherent models based on a minimal number of assumptions. And the problem is that any presumption destroys the basis of objective inference. So we prefer here not to rely on any assumptions, but only on the empiricism of physics as perceived by the senses. Whether we have succeeded, we have to leave to the reader. And I have to say that the work as it stands, I think we'd be very happy for input to see if we can refine it and qualify it a bit more, perhaps. The difficulty is the use of any assumption means the outcome of a line of reasoning may have originated from the assumption, leading to the anti-foundation axiom, which Russell called an impredicative definition, and Hermann Weyl a vicious circle. And an example of this vicious circle is we found in the doctoral thesis of the late Stephen Hawking. From the beginning, he assumes the existence of irreals like zero and infinity. And not surprisingly, that leads to a belief in the Big Bang from postulated zero and black holes from postulated infinity. As it happens, category theory comes to the rescue of black holes as a free functor valued category, but it cannot support the Big Bang. Empirically, nowhere in the universe can be found nothing. Free functor valued category is a category which has got a free functor which gives you creativity, but there's always, it's partnered under a jointness with an underlying functor which controls the actual values that can be created stably. Euclidean space is not connected naturally, so the elements for sets are independent one of another, and some arbitrary functions like the Peano conjectures can be applied to relate them at will, but the universe is inherently not arbitrarily connected, but strictly related by a higher order relationship. So we believe that the functions map to functions, and then the result of that, a functor is mapped to another functor. So we need to rise above sets to category theory, which in its pure form is a metaphysical language, as opposed to the modeling language of set theory. Another problem with set theory is that a set cannot be a member of itself, whereas we think that's an important part in natural representations. So a self-reflexive category can be one of its own objects. So recursive structures like that, self-reflexive structures, are much easier to achieve in category theory than in set theory. Right, so we've got these three realities defined, and the ordinary numbers are on the lowest rung, and then we go up through two other levels to a metaphysical reality. So I'm going to give a diagram for that. As a collection of categories, the universe may be viewed as a staircase of three rung processes interlocked by a jointness as a downwards direction from the meta-meta level. These are continuously related downwards exponentially. Right, so this is the diagram that we have, and it is the downwards direction from A to the C to B to the A. Now these constructions like A to the C are important. These are exponentials. That is all the arrows from C to A, and that is all the arrows from A to B. So these are exponentials, and they give connectivity in the category theory world. They're the basis of Cartesian closed categories and of the topos. So we say, what we're saying or claiming is that the process A to C to B to A is under the control of the three-level heighting logic. So on this top level, we have metaphysical reality, which is the category C. And as we shall see, that only includes three things in the end. One, the Euler number E, and pi. So we think we can build everything from these at the lower levels, but they're obviously under the control of the three-level category definitions. Right, so we have this as logic gate, which may be interpreted A, integral with its context C, such as the rest of the universe, precedes B. So that means that that C times A, which is A to the power of C, precedes B. This is mutually and conversely true with the requirement that C precedes the inference A implies B. And all this is really saying is that the arrows from C to A, that's that bit there, precede the arrows A to B. That's basically what that diagram is saying. So we've done many three-level structures before, and this would then be the metadata, this would be the metadata, and this would be the data itself. So we have done something like this before. So this would be in a relational database, this would be the basic data values, this would be how you define those values, and this would be the abstractions linking those constructions to, well, what they are in real-world abstractions. That's the basic idea. So formally, this is the inherent internal language of a pure topos that has exponential objects, but no ordinary numbers. That is empirically the same as the universe. So the pure topos, yes, there are, I think there's well over 100 types of topos. Pure mathematicians have played around with these to enormous effect, but some of them, like the earlier Grothendieck version, logic relies on set theory, have more Boolean type topos, whereas ours is a heighting where you can have more openness in the structures than in Boolean. The important thing about heighting, in Boolean, not is true. In heighting, not is not necessarily true. So heighting has, the negation in heighting is more complex, more subtle, and perhaps meets the natural world, models the natural world, or represents the natural world in a better way than in set theory. So that's the diagram that we're going to use really for the rest of the paper. I'll just check the time. Right, so that's an important diagram. So ordinary numbers all belong in the lowest rung as axiomatic models. So they are all in the model of reality. Whitehead insists that a system of axioms needs to be independent, consistent, and be proved to exist. And Peano needs around a dozen axioms to establish the arithmetic at the infinite level. Zero is assumed as natural, but never a successor number. So closure is also assumed under the equality relations, reflexive, symmetry, transitive, and the injective successor function by induction. But there are issues over the mix between first and second order.
Excuse me, one more question. What does it mean for a number to be found in physics?
That's a good point, as opposed to arithmetic. Yeah. I think there's no doubt that numbers in arithmetic are our ordinary numbers. If it's a number in physics, I think that the answer would be what is the typing of that number? How can it be related to more fundamental number systems? So,
well, it's that I get confused. I think you said something like Newton's law, square law, shows that the number 2 occurs in physics. Is that the way you speak? I'm trying to understand how you speak.
No, I don't think that's quite right. The point is about Newton is that all he was doing was doing the mathematics of Euclidean space. And so that's what his 2 is. But what numbers, that's an example of the numbers in the mind. The phrase numbers in the universe is perhaps a bit ambiguous.
Yeah, I think that sentence with the number 2 in is not actually core to the paper. So if you don't mind, Lou, I'll press on.
Please.
Yeah, and we'll come back to it later. I must, that paragraph, I didn't actually, I haven't internalized myself that perfectly. So I don't want to defend it strongly at this stage or get involved in discussion too much. Is that okay? Yeah. Right, so saying again, the integers are make-believe, only existing in the mind and not to be found in physics. And although claimed real, the ordinary numbers include the integers, the rationals, and the irrationals, all of which can be represented by a point on the straight line. And there's still just the little problem, there's no such thing anywhere as straight lines other than in the mind. Right. Yes, the equal sign is probably the most, one of the most difficult to pin down, I think, in science. In category theory, the equal sign isn't actually part of the theory, because we say that things are isomorphic, they're indistinguishable, but we don't actually say that they are equal. We don't say that things are identical, because we don't think that is possible. So the unique up to natural isomorphism is the way category theory speaks. So the equal sign is a difficult sign, I think, in science. Innate connectivity in metaphysics imposes a comprehensive relationship between entities, represented by the arrow in category theory, covering all possible interpretations. One such effect is every entity may be thought of as a first order model of every other entity, and no model can be treated as wholly wrong. So that's a very sound point. All models have some strong points. Belongs to Whitehead's every truth is a partial truth, as empirically there are no 2 identical entities in the world. The use of the equal sign is a sleight of hand, because all is process. Whitehead claimed that 2 times 3 equals 6 should be read as 2 times 3 becomes 6. And that, of course, is how computing science works. I mean, when you have computer programming, you don't say that you don't generally say 2 plus 3 equals 6. You assign the result of 2 times 3 to some variable. So it's not a popular construction in subjects like computing. So clearly the left and right-hand sides of the equation, 2 times 3 equals 6 are not the same. There's some assumed interpretation, and this is one reason why Whitehead and Russell in their Principia had such difficulty in proving 1 plus 1 equals 2. The point being, how do we know that each of the 2 ones have the same definition? Do any numbers exist? So so do any numbers exist? Well, I've got a list of some remaining possibilities. We've got 0, 1, square root of -1, which of course we write as I, E, pi, and infinity. And what we're looking for, when I say do these numbers exist, what we're looking for is numbers for our top level in our metaphysical construction, which will be able to act as the abstractions for deriving other numbers further down the structure. So we're not saying that the number 1 or 2 or 3, sorry, the numbers 2, 3 or 4 don't exist. It's just they're going to be at the bottom level, below these more fundamental numbers. Right, ordinary number 0. Yes, so we think that's a mathematical or mythical creation as a cardinal number, and again, not to be found in the physical universe, and therefore not proved to exist. The arithmetical zero has been invented many times throughout the world because of the need for a placeholder in any consecutive number system. So the algebraic zero, on the other hand, was invented by the early English polymath Thomas Harriot in the 16th century. And he had some doubts about it because, like all equations in physics, there is always some issue whether the terms are pure numbers or have implied dimensions. This might relate, Lou, to what you were saying earlier about the issue in physics, whether terms are pure numbers or are more complex in their basic structure. To be safe, Harriot would write a quadratic equation as ax squared plus bx plus c equals 0, 0, 0, but realized that this was really an ordering for which he invented the sign, although it does not help to relate the cardinals and the ordinals, which have no natural correspondence. So, so that's one problem with zeros. There's also the problem with nulls. You get things like null sets, and you get empty categories and things like that. And these can give problems in quite a lot of unnecessary problems when people are first starting out learning these subjects. So they have difficulties often swept under the carpet. The isomorphism with the null set is anomalous. That's one problem. And in databases, my own, of course, original subject for earning my money, null data values are quite a problem. Relational data model, you can end up with null data values all over the place. So by the closed world assumption of relational databases, any tuple not in the relation represents a false proposition. But that doesn't guarantee integrity of the tuples that are true. And in particular, the handling of nulls poses many semantic problems. If you treat them as data values, you're going to end up with, I mean, can you join R is one null equal to another null? And SQL ended up with quite a lot of complex rules on nulls as to whether circumstances in which it was possible to relate them. And nulls can be there for things like missing but applicable, missing and inapplicable. If it's missing and inapplicable, then perhaps you should change your data structure. If it's missing but applicable, well, this is the familiar N stroke A in spreadsheets. The problem is, if you have a lot of nulls, it makes the system undecidable. And this was quite, Northumbria University was involved with this for a while with David Livingston, one of my former colleagues at Northumbria University, developing a relational model that did not permit nulls. So zeros and nulls cause problems. Got some others listed here with nulls. The Council of the Royal Statistical Society has recently raised queries about the null hypothesis and significance testing. Even more recently this year, the Royal Astronomical Society has announced doubts about the 0-point constant of the bolometric correction scale, which is the basis for relative luminosity in astrophysics. And this has far-reaching effects on reported work for 80 years on luminosity, with knock-on doubts for understanding topics like the accelerating expansion of the universe and general cosmology. So there are problems with these nulls. So we're not counting zero nulls as what you might call first-class numbers for the top rung of our structure. Numbers -1 in infinity, they belong to the lowest rung of reality. Numeral 1 only provides a label to distinguish positive and negative numbers. Its imaginary root I goes further but cannot be said to be truly a natural number. Infinity we consider as a model in mathematics and does not exist anywhere in that form in physics. And for 50 years, mathematicians have believed that the total number of real numbers is unknowable. However, the corresponding concept that Whitehead calls unbounded is available in category theory, again as our free functor valued category and able to cope with the open closure. That's what a free functor value category gives you. It gives you openness, creativity, but does provide bounds, does provide closure to give a very useful view. However, we now come to one of our numbers at the top level, number one. Number one is the top of the three-level ladder as a really, really real number. How many true ones are there in the universe? Well, we would say there's only one universe, namely the universe itself, and we use the self-reflective image of that universal one to carve out and designate one of anything in the world. So one is the terminal object in category theory, and you can specify in these exponentials, you can use one, and that will, so one, if you have n to 1, that would actually give you all the numbers from 1, the universe, to your natural numbers. So it would actually define the natural numbers, but in the context of the universe, rather than giving them perhaps a greater foundation. So you can carve things out from the universe using the exponentials. The use of one is viable because the really, really real number, E, relates objects recursively top down. E is related to 1 because these exponentials actually can also be used for linking one category with another. So it's not surprising that E is so fundamental to be needed in many physics energy equations, where again it self-reflects down examples of mass energy in the universe. So if we go back to our structure, if we add 1 and E at the top, we can actually, through using exponentials and the fact that 1 is a terminal object, we can, representing the universe initially, we can carve out all sorts of other numbers as we move down the structure. That is the idea as I understand it. Now, pi is a bit different because pi, it really appears to be natural. Pi appears so often in nature and in many, many theories that if we consider our numbers at the top level are natural, then we have 1 and E, which we think are undeniably natural. They're the basis of the Cartesian closed category and the topos in category theory. Then pi isn't in category theory. You might, perhaps it should be, but pi appears in so many equations for geometry with curvature, such as infinite series and products, integration in mathematics, and in physics, from the simple pendulum to Einstein's field equations, the cosmological constant, Heisenberg's uncertainty principle, electromagnetism, Kepler's laws of planetary motion, etc. So we've really given weight to the enormous experimental evidence and theoretical evidence that pi is a critical part of our scientific world. So, Mike, well, we have got an idea here. Understand anything in fundamental science, unless we can explain the ubiquity of pi suggestion. It's not too well known. There is no equation for the perimeter of an ellipse. It cannot be accurately calculated or drawn in 2 or 3 dimensions. If you're clever, you can calculate it approximately, and the closest seems to have been evaluated by the prodigy Indian mathematician Ramanujan, 1887 to 1920. So pi is slightly different in its for the reasons for its placement in the top level. Oh, I've gone the wrong way. Yeah, right. Right. Yeah, so here we have the top numbers, 1, E, and pi. So number 1, top of the 3-level ladder, is a really, really real number. And I think, have I got that? I think I've done that. Right, so that's our basic idea. We have these 3 numbers at the top, but they are really, really real numbers. They lead in, 2 of them lead in category theory to the definition of everything below in a structured manner through from the metaphysical numbers to the physical numbers, then to the ordinary numbers. Pi is there because of its apparent natural involvement in so many areas. So I'm going to finish up with some reason why we need to get away with first order methods. They've been extremely successful for 3 centuries in dealing with local systems, but become unnecessarily complicated on attempts to extend them at higher order for global systems. And I think one of our views is that a lot of things could be done locally, quite adequately, but as our science is getting more complicated, more interdisciplinary, more interrelated, we need to have better tools for linking these systems together. And what we've done is we've tended to make ever more complicated systems, first order systems. And a lot of the magic to make them acceptable to people has been to put computer programs into them to run the things. And people tend to think that computer systems provide valid answers, or it must be right if it comes from a computer. And so I think you get answers out from these very complicated computer systems. But if they're inherently first order, do they really handle the interactions between different subsystems in a properly balanced manner? So limitations, bottom level of science to be reviewed as it's blinkered. Common views, the current universe was initiated by the Big Bang, by quantum fluctuations. That seems to require quantum mechanics to have preceded the universe. Does then continued up to today by some process of evolution, with many universes postulated, all posited firmly on the existence of Peano's number system. So when, of course, I've got this top level of 1, maybe that assumes that we do have one universe at the top. But of course, people have postulated many different types of universe. And so it may be there's quite a lot of complexity in that top level as it feeds through into the second level, which is the physical numbers, into depending what type of universe you are dealing with. So the one that deals with the generic universe, you could have different types of universe to give your physical numbers in the second level. That's quite a possibility. I'm not going to read out all of these. You can look at this. It's in the thing that Mike circulated, and it's also on the web page. So this mapping down from the top level, like the 1 for universe, could be quite complex. Could involve different types of universe with different views on numbers and number systems and things like that. So there is quite a lot of complexity there. Right, so this is a bit like the IPCC with their red warning on climate change. So we've got some red scientific health warnings on 2 pages, which I think will finish the talk. Yeah, that's right. So basically, it's where areas are being done in first order, and we think we should be using higher order. So quantum mechanics elevated to quantum theory, linear differential Schrödinger equation to use as a model to form a misleadingly stable system instead of the higher order topos. Sorry? Sorry, did somebody say anything? I'll carry on. Quantum computing, the quantum bit instead of the higher order quantum monad. So we think that they should be using a a higher order structure, the monad rather than the bit. Statistics and probability. First order statistical models can be way out when applied to higher order phenomena. Compare grossly wrong predictions for the COVID-19 virus. Newton and gravity. Whitehead dismisses Newton's first law of motion because of Euclidean limitations, and the second law is a circular argument. Newton's third law of reaction needs to be recast with higher order Heiting logic. Einstein's special powerful theories are neither right nor wrong, but they could perhaps benefit from being treated at higher order. Chaos theory could introduce higher order phenomena rather than trying to model them at the first order level. Pure mathematics does a lot of symbol bashing. Whether this is the best way to do things, invest a lot of public money, is Leicester University, for instance, has closed down its pure mathematics department, but it still has a very active category theory group. So that is perhaps the way things will go. And we have information technology and AI. Climate change, well, this is, I think, one of the prime examples where you have enormous computer systems being constructed, tremendous amount of interoperability, and is it all being brought together with effects like the geophysics all being integrated in a proper way? Have to have some doubts. And the laws of thermodynamics are entirely axiomatic and are anomalous. Right, that completes the talk.
Okay, thank you for that talk, Nick. Any questions? Can you unmute? Not unmute. Can you get off shared screen, please?
Here's a question. What is the role? What is the place of?
You want me to stop share?
Yes, stop sharing screen. Yeah.
Right.
What is the place of the square root of 2 in your cosmology of number?
Square root of 2.
The square root of 2 is can be drawn on a straight line. So it's an ordinary number which doesn't exist other than in the mind. It's not like the perimeter, which you can't draw.
You place it on the side of the mental rather than the physical.
Yes.
Oh yes, yeah, well, yes, because it's on a straight line, and straight lines don't exist. You can do it on a straight line, can't you? I mean, it's a point on a straight line, and a straight line doesn't exist in the physical world. So we're keeping to physics, really. I'm sorry, I'm in a rather noisy ward.
So in your cosmology, the square root of 2 is not physical.
No.
Yeah, and it's, well, so unless you want things in the mind to be physical.
Well, it's just that usually people think of the square root of 2 as quite physical, being the length of the diagonal of a square.
Yeah, well, again, you see the square is straight lines. There's no such thing as a square in the universe, because the universe is non-Euclidean.
Well, all right. I will ask the more general question then.
Can somebody mute?
I want to ask one more general question and then quit asking. What do you mean by the physical?
What do you mean by the physical?
Yes.
Well, as Nick described it, it's what's perceived with the senses. Facts. See, I mean, there are statements of facts and statements of belief. We're dealing with statement of facts.
There you go. Northerners in all of us.
Much of it.
As I said, I will only ask the question and make no further comment.
Okay, thanks. Thanks for your question. Nice to see you.
What's the evidence
Barbara,
for
with
saying
great respect, can somebody mute wherever that source of noise is coming from? It's very intrusive.
No,
I'm sorry. I'm sorry. It's me. I'm in a very noisy ward in the hospital.
Yeah. So the circumstances, no, we cannot.
Yeah.
No. I quite appreciate that. And I hadn't understood the situation. My apologies for even raising it. Sorry.
So could I ask why you claim the universe is definitely non-Euclidean? Because experiments recently, well, 20 years ago, seem to suggest it was Euclidean.
Well, like the Cavendish experiment, that kind of thing, but it's always approximate. I mean, students, when they
all experiments are approximate.
Yeah.
But we don't know that it isn't Euclidean.
Well, but again, it can't be perceived by the senses. I'm taking standard cosmologists to say it's not. And it seems reasonable that there's no reason why it should be.
No, recent cosmology experimental work says that it's Euclidean. That's why we got a flat universe.
No, I think since then, John Barrow, unfortunately, died from COVID, says otherwise. You'll find the reference to him in the paper.
Well, certainly, I'm talking about the experiments, which are still claimed to show that the universe appears to be Euclidean.
No. The universe is spatially flat. There's certainly matter in it, which means space-time is curved, but it's spatially flat to at least
spatially
1%.
flat. That's what we mean by Euclidean.
It still has, yeah. Okay, you mean the spatial part is Euclidean?
Spatial part is Euclidean, yeah.
Okay.
Anyway, any further questions?
This is Mike. Nick, I would like to congratulate you on fantastic work. I really, really appreciate that. And I hope that the idea of moving towards integrating, shall we say, bits of knowledge which have got different bases in some sense, will be successful because, as you pointed out, just to give you an example of computers, you know, we cannot rely on what comes out of these things because all of the, I mean, on Monday morning, I usually go to the East and say, Mea Maxima Corpora, I was working on this stuff for 25 years and it's still much onto an unreliable help.
Thank you.
Yeah.
But I mean, can we, if we can accomplish any
We've lost Peter.
Reliance on computers, and can we put any reliance on people? I mean, how do you propose to teach this system to members of the human race? Particularly school children, for example.
I think school children would find, I mean, these are basically handles, some of these things on it. So one, the universe would be your introductory handle, and then you would take, you would identify parts of the universe that you wanted to select for further study and so on. So you can't partition the universe. You are selecting parts of the universe for study recursively. I think school children could easily adapt to that. You don't have to give them full-blown category theory, I think, too.
And it's hey John, why don't go? Yeah, because our hands up haven't been noticed at all. You go first, John. You're ahead of me.
Thanks, Nicola, and thanks Nick and Michael for a lovely talk. Enjoyed that. I just want a couple of things. One is, would you like to comment on whether or not reality might be partially imaginary?
Yes, what is reality?
It just depends on what you mean by reality. These are different types of realities. I mean,
to be specific,
of the mind as in all the numbers, for example. But
well, to be specific, if we take second order cybernetics, we want to have some process which comes back to its starting point. If we're going to something like that, we'd like to have something that allows things to go round and round in circles. And the classic
cybernetics was a bold attempt to escape from first order, wasn't it, with the systems theory. But again, you see, it's a matter of whether you're talking about a statement of fact or a statement of belief. And so our world as we perceive it is a statement of belief, which is it's the other way around from chaos theory, whereas the real world, in the two-slit experiment, for example, the real world, the exact world is the coherent light source, and the screen is our perception, how we perceive it. Again, it's a statement of belief, not a statement of fact.
Yes, but in the reality of the two-slit experiment, there are certain points on the screen that don't exist, and there are points that do exist, a set of them, so that don't exist for that coherent light source. And likewise, if one considers elements of reality which are interactions, those interactions take place through a process which is one of returning to one. So coming back to your first number, but that return to one requires something which is a proper inverse. And so if we're looking at processes that exist at real numbers, we should surely also consider things that are their inverses. And if one wants to get proper inverses for everything, then one perhaps needs something that's at least imaginary in the sense that it's the square root of -1. I think there's an argument to be made for that. That reality then is partially imaginary.
Yes.
Or must be in order to have return.
So you're suggesting that should be added to the top level, the top run?
Well, I was thinking, I loved your top level of 3 because they're 3 of the elements in the old famous formula e to the I pi plus 1 equals 0. And I loved your discussion about equals as well. I think you're absolutely right. There are at least 10 different sorts of equals. So that was a great thing to bring up. But you're kind of missing the 0 in your top level thing. You're missing the 0 as one of the numbers that people would take to be really real. And I remember losing an argument on whether 0 or 1 was most fundamental quite quickly.
So John, you would say that we should include in the panoply of really real I.
No, because clearly that's defined as being completely not real, almost by definition. But on the other hand, in terms of describing reality, yes, there being a difference between real and reality, of course.
So we would need to change the legend as well. Which I think Lou is worried about, this phrase, physical reality. So there is some suggestion there that, yeah.
Curiously, I have no trouble with reality. I only don't know what is physical reality.
Yeah, no, it's funnily enough, I had the same problem a week ago. I was talking to a Whitehead conference and I was going on about physical sounds, and somebody at the end said, "Why do you call them physical sounds? Why don't you just call them sounds?" I thought that was a good point.
Okay, Nicola, have you got a question?
Yeah, well, I mean, actually, I was interested the way you came in with the imaginary, John. Yeah, because my viewpoint obviously is of the great oneness definitely includes imaginary and imaginal, which is different. I know one thing. I'll tell you what, Nick, I'll ask one simple question, because this is just to do with actually kind of getting my head around what, how category theory is, when one has these beautiful diagrams. So if you go back to your picture with the metaphysical reality C, physical reality A, model of reality B, and you have a little, you have like the cross product C cross A, which looks like is equal to or less than B, and then you've got one underneath saying that C is less than or equal A implies B, i.e. that's the way that I would normally read it. And you were talking about perceives, you were using the verb perceives there. And this would be a way that I might actually understand what these category theory diagrams are actually supposed to be doing. Because I wish it, so could you explain, go through that again, what the perceives is? Who's perceiving what there?
It's the arrows that are, it's the, I'm basically, it's very simple what it's saying. It's saying that the arrows from C to A precede the arrows from A to B, so it's all linked up.
The arrows from C to A.
That's A to C is the arrows from C to A. So that's the first arrow in the downward structure.
Could you put up the structure again so I can actually see that? Are other people okay with this? Or
I think that might be difficult because
it's only standard heighting logic. I mean, you can read it in any intrinsic logic book. We have within it. It's not our creation.
No. I know it's not your creation. So, but it's just actually, yeah, where to find this to actually, because this is one of the things about any mathematical thing. If you read a, it's one of the interesting things. I mean, actually, obviously, stuff is on the web now. But like to read a mathematical book, if you cannot actually say it out loud, to get it is very difficult. It's really, it's.
I thought we did have an explanation on the bottom left of the diagram. Unfortunately,
don't worry about it, Nick, because obviously this is recorded. I can replay it. So we'll come back to my.
Yes, if you get the slides from the web page,
yeah,
then there is an explanation on the bottom left, which spells it out in quite a lot of detail.
Okie dokie. Yeah. So
what's the address of the web page, Nick?
Yeah, well. Yes, I'll put it up on chat.
Okay, we got
in a minute or two. Yeah,
we got the web page.
That's lovely. Okie dokie. That's super. Okay.
Thanks, Laurie.
So yeah. So what is?
You can get the slides off the web page.
Yeah. So
on the chat.
Yeah, it's this thing of like, you know, what reality is, what one is trying to. I mean, I have a number of problems. One is the idea that you can come to anything without assumptions. I totally disagree with this. I think, you know, that one's starting point has to be as a grown-up or attempted grown-up, one has to always be aware that we come with assumptions. Part of our research is looking into whatever we think we're looking into, but it has to be also looking into where have we been coming from? Where have we got that from? So I have a fundamental disagreement about the idea of not having assumptions. And then there's also another problem, yeah, this distinction of the physical, you know, I mean, obviously one can say that. So I presume you're saying the physical, which is according to the 5 usual senses. But of course, we know now, just, you know, from scientific evidence, but I mean, actually we would know it in other ways as well, that there are many, many more senses, just you know, neural senses. So there's a problem of the wanting to say that, you know, what's really, really real is what we can perceive with the 5 senses.
Doesn't matter.
You know, and
I think what you perceive is the first level. all the spiritual, etc., are at the top level. It's a relation between relations. That's where all what you're talking about is.
So you're saying that the spiritual is within that top level.
Yes, that is the top level.
Right. Okay. All right.
I mean, whether it's religion or it doesn't have to be religion, it can be secular.
Right.
But there's always a terminal object. It's natural to have a terminal object, and as humans, we have terminal objects. So your terminal object might be the tenet of atheism, but it's still a terminal object.
I would prefer it to be called a terminal subject.
There is a
superjet.
I use
a source subject. Yeah.
Parker Rhodes used.
John Torday wants to bring something in as well. So yeah.
I don't know if this is helpful, and I'll talk about this because I think that one way to look about this is it's Bohm's explicate order. So when life began, it defined itself, it differentiated itself from the implicate order. And so the questions that are being asked are all about how we are able to cope with the physical reality. It's so in terms of imaginary or imagination, that's the capacity to conceive of what we don't actually, we're not composed of. So that's the anticipation is important in terms of survival. So there is a way in which to understand both the real and the imagined in the context of evolution, in my opinion.
Okay.
I agree with you, John. I mean, I think that we wouldn't be intelligent beings if some process wasn't going on that matched up what's going on in our brains with reality.
Correct.
And enabled us to survive.
Right.
If I reach out and touch something in front of me, if I don't find it where it actually is, then I'm not going to survive.
Right.
And that's the basic property of sentience.
Yes.
In fact,
yeah.
I take to some extent an opposite philosophical view to Lou, because I think for me, I take Aristotle's guiding principle that credit must only be given to theories only if what they affirm agrees with the observed facts. And so I'm not really interested in any, in science, in any other system, unless it actually predicts something that is very close to the observed facts. I think for me, mathematics is just a language that is just something that has evolved out of the evolution of intelligence that makes all the mathematics that we have suitable to give explanations for many of the things that we're all interested in doing. So I'm very happy to listen to you all, because it's all part of your experience, and for me it's all valid. To go into my system and see what comes out. So
okay, thanks, Peter.
I'm much more interested in what's going on in my brain and your brains than I am really in the way it can be represented in various forms.
I think we should close.
We've got to be able to get objects in the information about objects into our brains, and the question is, how is this actually done, and how has it evolved to give us?
I think we should think about closing the formal discussion.
Yes.
Yes, we need a break. Yeah.
We need to break. We'll close the formal discussion. Those who want to carry on discussing can do so, unless Lou's very quick with what he wants to say.
Yeah,
Lou, you need to
unmute. Can you say something very quickly?
Sorry, I put a quote in the chat line from Buckminster Fuller.
Thank you,
I'd
Lou.
like to read it. You can think about it. An energy event is always special case. Whenever we have experienced energy, we have special case. The physicist's first definition of physical is that it is an experience that is extracorporeally, remotely, instrumentally apprehensible. Metaphysical includes all the experiences that are excluded by the definition of physical. Metaphysical is always generalized principle. And of course, this does not create a sharp distinction between the physical and the metaphysical. It tells what the situation is between the physical and the metaphysical.
Okay, thank you for that, Luke. We'll call it a break